Thank you. So there are three types of lies. There are big lies, and there are statistics. So as a starting point, please consider the following statement. In the Vatican City, there are 5.88 popes per square mile. This is not a lie. The statement is correct. And of course, something funny is going on here. We kind of know we expect to be one pope at a time. But if somebody doesn't know much about Vatican and popes, it might be led to think that there are actually many popes in the Vatican. So this is what the talk is about, the misuse of statistics in everyday life, or as a subtitle, how to lie with statistics. So just to be clear, the talk is not really about Python, and we're not going to do any advanced statistical modeling. And my only assumption about you as the audience is that you are good citizens, so you don't really want to lie using statistics, and at the same time you want to know just enough so people cannot fool you into thinking something that is not real. So there is no need, essentially, for any advanced math degree. Now, we're not going to talk much about Python, but just as an experiment, how many of you have any kind of knowledge in Python, any sort of basic or advanced or heard of Python, seen any Python? Basically everybody. Anybody feeling sick? No? Anybody feeling unwell? So everybody who knows some Python is in good health, right? So Python is good for you. So correlation is the first topic of the talk. Correlation as an informal definition. We already have it in the name. So co means together, and relation means something is going on. So a connection between two things, or two events, or two variables. A bit more formally, correlation is the measure of how strong this relationship between two variables really is. Often when we talk about correlation, we really mean linear correlation. So linear correlation, if you have two variables, x and y, it means we can basically plot x and y almost on a line. So if x goes up, also y is going up. That would be the positive correlation. And we can also have a negative one. So if x goes up, y goes down. Now to give you a more concrete example, you can consider temperature and ice cream sales. So intuitively, when the weather is nice, more people go out and more people buy ice creams. So essentially, temperature goes up and ice cream sales also goes up. And the way I'm describing this, basically, there's a cause and effect here. Good weather means more people going out and more ice cream being sold. In general, this is not always the case. So correlation doesn't necessarily imply a cause or an effect. It just implies that two things occur together. As a case study, you can also consider ice cream sales together with deaths by drowning. So when more ice creams are being sold, also more people die by drowning. So is ice cream really a killer? The problem here is that there is something behind the scene that is called a lurking variable. A lurking variable is a variable that we don't see, but it's kind of looking at us. And in the ice cream and drowning example, lurking variable is, again, temperature. So when the temperature goes up, as we said, more people go out and buy ice cream, but also more people go swimming, and so potentially there are more deaths by drowning. So ice cream sales and drowning are not directly connected. They are connected through the lurking variable temperature. One more example on lurking variables. If there's a fire accident, when you deploy more firefighters, the damage is bigger. So one might think, why don't we deploy less firefighters? Well, the problem is how big is the fire? So if there's a big accident, you deploy more firefighters, but at the same time, if there's a big accident, the risk of damage is much bigger. So fire severity would be the lurking variable here. So when we try to explain correlation in terms of causation, there are many options that we can consider. So if A and B correlate, either O causes B or B causes A, or A and B together are the cause of something else, or something else is the cause of A and B, or maybe A and B are connected through C as a kind of transitive relationship, or maybe there is no connection at all between A and B. So I guess at this point you appreciate that it can be complicated. So just for fun, we can look at some variables that correlate, but they're quite difficult to explain. So number of people who drown into a pool over the years, and number of movies with Nicolas Cage. Maybe Nicolas Cage is bad luck. In red, consumption of margarine, and in green, number of murders by blunt objects, so maybe margarine makes you nervous. Nowadays, it's quite easy to blame Facebook for everything, but we can see number of users of Facebook, when they go up, also the national debt of Greece goes up. So Facebook not good for the economy. Is important. Number of users of Microsoft Internet Explorer. If less people use Internet Explorer, less people also get killed. And my favorite, chocolate consumption and number of Nobel Prizes. So you can see almost all the countries are on this line. The more chocolate you consume, the more Nobel Prizes you get. For some reason, we have a couple of outliers. So Sweden, they have many more Nobel Prizes than expected. Who knows why? And Germany, stereotypically very efficient at everything, but not very efficient at converting chocolate into Nobel Prizes. Next topic, slicing and dicing your data, also called the Simpson's paradox. It was described by somebody not called Simpson, but for some reason nowadays we call it Simpson paradox. We can understand the paradox with an example. So if we look at the University of California and the admissions in the 70s, you notice that basically a much bigger proportion of men are admitted compared to women. So one might ask whether there is some sort of gender bias going on here. Once you break down the numbers into individual departments, there are more than 80 departments here, and we are reporting just a few. When you look at the individual departments, you notice how, for many departments, the ratio of women being accepted is much higher compared to men. But then when you look at the number of applications, you notice how the groups are really skewed. So many more men apply for departments where the acceptance rate is higher, for example, Department A, and a smaller number of men apply for departments that are, like F, much more competitive. And women behave kind of in the opposite way. So we have many more women apply for departments that are more competitive. Essentially, what's happening here is that we have a highly skewed distribution across different groups. So the numbers that we see here are correct, and the numbers that we saw previously in the aggregation are also correct. But because of this distribution, we observe this weird phenomenon where the numbers here are telling us a different story compared to the aggregation. So if you have an agenda, you can basically choose which one you want to show. And if you don't have an agenda, you should use the paradox to better understand the problem. Next, sampling bias. So sampling is the selection of a subset of individuals from a bigger population. And the purpose is to make some estimate about something about the whole population. And we do sampling because it's cheaper and it's faster compared to computing something against a bigger population. Back in the days, sampling was useful because we didn't have a lot of computational power. Nowadays, we have more computational power, but we also have bigger data sets, so sampling is still useful. Bias. So bias in everyday language has some sort of negative connotation. Typically, we talk about bias as having a prejudice, if you are biased against somebody or against a group of people. Maybe there is a cultural aspect to consider. In science and engineering, on the other side, we don't give any positive or negative connotation to the word bias. It's simply a systematic error. So a sampling bias is an error in your sampling method. As an example, Dewey defeats Truman. This is Truman, President Truman, and the day after he got elected, President of the United States, he's smiling and waving a newspaper saying the opposite, Dewey defeats Truman. So what happened here, the newspaper printed the wrong headline, and it happened because they trusted some phone survey that they did before. So they phoned people up, who are you going to vote? People give answers, and then based on the answer, they came up with the headline for the newspaper. The problem is 1948, so who owns a telephone? Well, not the general population. So if you phone people up in 1948, the people that you can reach are not really representative of the general population. It's similar to the opening question on who knows Python and who's feeling well. If you know who knows Python in a Python conference, you can respect more people than the general population. As a special case of sampling bias, there is something called survivorship bias. This is when you focus on the survivors and you forget about everybody else who didn't make it. It's like looking at a lottery winner and thinking, I should buy a lottery ticket as well. And you forget about all the people who bought a lottery ticket and didn't win. And nowadays, basically, all the motivational speakers, they will tell you, well, you don't need a college degree. Look at all the billionaires. None of them have a college degree. They are all dropped out from college. So should you quit studying? Well, talking about bias, I'm biased myself, and my answer is no, but you can decide who to focus on. Next topic, data visualization. Data visualization is a big topic, and it's a very powerful tool. So it's a powerful tool for us as a data analyst or researcher or whatever, just to have a better understanding of our data. And it's a powerful tool also to communicate the results to users who are less technical. So from a data analysis point of view, you can look at this example of 4 different data sets. They all have the same summary statistics. So the average for X and Y is the same. The variance is the same. They all have the same sort of linear correlation. But once you plot them, you see how different they are. So the suggestion is you should always plot your data and not just look at the summary statistics. And that's for the data analysis side. For the communication of your results, as I said, data visualization is a very powerful tool. So in this picture, some newspaper is reporting some sort of court case decision, and they're showing who's in favor and who's against. And you can see the first bar on the left is much, much higher compared to the other 2 bars. So it looks like the Democrats are much more in favor to the court decision compared to the Republicans. But then, if you look closer, you see how the axis starts from 50 rather than starting from 0. So once you put everything in perspective and you make the chart looking like it should look, you see how the 3 bars are basically pretty much the same. All the numbers are in the same ballpark. So that's one way to kind of misrepresent reality. Guns in the US, a very hot topic at any given time. So is the number of gun deaths in Florida. And in 2005, Florida introduced a law that is commonly referred to as stand your ground. Basically, if you trespass into my property, I can shoot you and use unnecessary force. And here they're showing how in 2005 they introduced the law, and apparently the graph showing us that the number of deaths goes down. The graph, for some reason, is starting from 1,000, the y-axis, and goes up to 0. So the correct graph should be upside down, and you see how in 2005 the law was introduced and the number of deaths was spiking. So literally, the reality is upside down. This was coming from the Business Insider, and the visualization was produced by Reuters, so later on they published the correct version, but they forgot to apologize. Well, politics is a nice playground for data visualization. So is Renzi a friend of the lobby? So being friend of the lobby is bad. So if you don't like the results of your survey, what you can do is take the proportion of yes, 44%, and show it as a tiny slice. So 25% and 36% behind the journalist is much bigger than 44%. And sorry if you pay the license, the TV license in Italy. I pay my TV license in the UK, and things are not different over there. So this is a leaflet from some sort of election propaganda. In the UK, the system is first past the post, meaning the first party in local circumscription will win the seat in parliament and so on. So essentially, the narrative is always, from the mainstream parties, is always, you shouldn't waste your vote on the small guys, you should vote for us. And here the conservatives are telling us you shouldn't waste your vote on the far right, the UKP, you should vote for us. But the graphic designer of the Conservative Party thinks that 42% is smaller than 32%. Just to make it politically correct, we can look at all the other mainstream parties. So the Lib Dem, you can see the leaflet on the top left. The yellow column is the Lib Dem, and they are kind of catching up with the Labour, almost. So you might be fooled into thinking, yes, I should go to vote, otherwise the others are going to win. But once you plot them correctly on the bottom right, you see how the yellow bar is much, much smaller and not very impressive compared to the red bar. And finally, the Labour Party. So the narrative is the same. It's a two-horse race, so don't waste your vote on the smaller parties. So the Labour here are telling you, don't vote for the Lib Dem, because it's a race against the Conservatives in blue. Once you plot the real chart, it is a two-horse race, but they forgot to include the Green Party, which is the actual second contender. So literally, in the leaflet, the Green Party disappeared. So yeah, a whole lot of different ways to deceive people with visualization. That's because people don't really read the numbers, don't read the research. They just look at the picture, and if the picture is something impressive for you, that's the message that you get. One more topic, a bit more technical, but we're not going too much into technical details. So statistical significance is one of the biggest misnomer, probably, in science. That's because in everyday language, significant also means important. So when the media reports some research result as statistically significant, they mean something else. So statistically significant results in statistics or in science in general, they just mean that we are quite sure about the results being reliable. So they are less by chance. Doesn't mean the results are big, doesn't mean the results are important, and doesn't mean the results are even useful at all for decision making. It simply means we are more sure about the results. So again, when the media mentions something about being statistically significant or just significant, what do they mean? Do they mean it's important, or do they mean we are sure about the results, or do they mean anything else at all? The notion of statistical significance is tied to the notion of p-values. The P stands for probability, and the p-values is, it took me a long time when I was a student to understand p-values, and I would like to tell you that I truly understand p-values, but I'm still a bit shaky. And if you are like me, you're not alone. There's a whole huge Wikipedia page about what the p-values is not. So let's see if we can upset the statisticians and give some sort of definition. The p-value would be the probability of observing our results, or something more extreme, when the null hypothesis is true. So null hypothesis, hypothesis testing, a whole lot of things I'm not talking about. The highlight is that these are probabilities, So it's not about certainty. So there's a probability that the results are correct. Often we talk about p-value with an associated cutoff threshold, which is commonly 0.05, so 5%. It could be something different from in different fields, and that's completely arbitrary. So different fields, maybe they have different conventions. So p less than 0.05 means less than 5%. It means every one time every 20, the results could be completely random. So can we afford to be fooled by randomness every one time out of 20? That's the question. Connected to the p-values, we have a notion of data dredging. This is real dredging. Data dredging is also called data fishing or p-hacking. So conventionally, what you should do is you formulate an hypothesis, you collect your data, and then you prove or disprove your hypothesis. With data dredging, you kind of go the other way around. You get your data, and then you brute force everything until something interesting and statistically significant comes up. So you look for patterns first, and then you use the patterns to formulate and test your hypothesis. So just to clarify, looking for patterns in your data is okay. Using these patterns to create the hypothesis and then test the hypothesis on the same data set is not really okay. It's more like cheating. Fortunately, it's quite easy to kind of catch for an expert eye, but from time to time you still see papers where you have a feeling that maybe they're doing p-hacking. So, wrapping up, it feels like we cannot trust anybody. Well, the purpose of the talk was not to create the next generation of conspiracy theorists. The purpose was just to give you a flavor of how powerful statistics can be. Typically, good science, whatever that means, good science doesn't always make good big headlines, so you should kind of be critical about huge headlines and whether they tell the whole story. It's important to remember that nobody is immune. Nobody is immune from mistakes, so everybody can make mistakes, and everybody can also be fooled by big headlines or by stories that are not completely told. So I guess the important take-home message is you should get some basic knowledge of statistics, but you should also be healthily skeptical and ask questions. For example, what is the broader context? Who is paying for a particular study, especially when study about medicine and miracle cures? Should always be skeptical and ask the questions. And what is missing from the picture? Is there a broader context to consider? And in summary, probably the most important question is, so what? We have some results, so what? In research, often one result should lead to some more intuition and lead to something else. And also, as kind of a good citizen, as we mentioned at the beginning, the question should be, so what? I'm reading some headline, so what's going on? That's it. The slides are on my speaker deck, and I guess we have a few minutes for questions. Thank you very much.
Is there any question?
You all know anything about statistics? Yeah.
About the p-hacking,
Yes.
Is there anything like the Bonferroni correction to check out if I'm trying to cheat and prevent it? Thank you.
The short answer, there's a lot you can do. Typically, so I'm coming from more of a machine learning background. The classic mistake is using the same data set for training and testing. That's what happens. And you can see the same pattern basically being used over and over. Off the top of my head, what I do, I kind of look it up, so the specific techniques for addressing the problem, I deliberately choose not to remember them by heart, and I just look them up. But the way I approach the problem is just trying to understand whether we are using the same data set in two different steps. So having a separate validation data set is what people should do. So basically validate your hypothesis against new data to make sure that the hypothesis holds.
Any more questions? That's it. Thank you.
Thank you.